Hi everyone. In this video, I'm going to provide a demonstration of linear regression using Stata, and I'm going to be emphasizing the use of the drop-down menus in Stata in order to carry out some basic analyses. Now, I'm not going to be going into all aspects of linear regression, but what I wanted to do is just to show you some of the functions in Stata and go through and offer a little bit of an interpretation of various pieces of the output. So you could kind of think about this video as sort of a general introduction to linear regression with Stata. So what we have on our screen, we have basically Stata has been opened up, and I've already imported the data set, and you can download a copy of the data set by following the link that's provided underneath the video description. And the example that we're going to be working with is based off one that is given in Whitaker and Schumacher's most recent version of the text, Beginner's Guide to Structural Equation Modeling, the 5th edition. So basically, the analysis involves testing or predicting patient satisfaction level as a function of age, severity of illness, and severity of anxiety. So as we go through this demonstration, all of the tests that we're going to be carrying out, we're going to maintain a nominal alpha level of 0.05. So this is, again, this is our basic linear regression model that we're going to be testing. So we're going to be looking at the overall fit of the model by looking at the R-square value and the F-test in terms of testing the significance of the set of the predictors. And then we'll be looking at the individual predictors within the model in terms of their contributions. So to carry out our analysis using the drop-down menu, what we're going to do is go to the statistics button right here. We'll go to linear models and related, and we'll click on that. So linear regression. And then when this little box opens up, we have our dependent variable. I'm going to use the drop-down right here and select satisfaction. That's going to be our dependent variable. And then for our independent variables, I'll select the drop-down, and I'm going to click on age, severity, and anxiety. So you can see that as I select those, they fill in terms of the independent variables. Now, for this particular analysis, we're making the assumption that our predictor variables are all continuous. But if I happen to have a factor variable or something along those lines, then I would need to make sure to recode my variable into perhaps maybe dummy variables or some other type of variable coding in order to capture those factor variables. But we're just keeping things very simple for this particular analysis. We're just going to be treating all of these variables as continuous. So now when I click on the OK button, you'll see that we run our basic analysis right here. And so we get our basic output, and just kind of taking a look at our output, let's just highlight a few things. First off, you'll notice that over here on the right side, you'll see that we have the number of observations. We've got the F-test value as well as the p-value for that test. You'll notice that we have the R-square value that's given right here. We have an adjusted R-square that's given right here. So basically, as we're looking at this, the R-square value that's given, which is the 0.6854, which we have right here, this is basically indexing the proportion of variation in our dependent variable that's accounted for by the set of the predictor variables. So we're basically at this level, we're looking at the combined effect of all of the predictors within our model. What is the joint contribution in terms of explained variation? So if we multiply the R-square value times 100%, then we could say that the set of predictors are accounting for about 68.5% of the variation in satisfaction. Now, you'll also notice that with our F-test, which is up here, so we have the F value, which is 14.53, and we have a p-value that's given right here. We're using this to test the contribution of the entire set of predictors in terms of accounting for variation in satisfaction. So the null hypothesis for the F-test is that the population R-square is equal to 0. The alternative is that the population R-square is greater than 0. So if the test results indicate statistical significance, as it does in this particular case right here, then that's going to, what we're going to do is we're going to interpret this to mean that the population R square is greater than 0. We're basically making that inference that the population R square is greater than 0. We might also say that, because, if our population R square if we can infer it to be greater than 0, then we would expect that at least one of our regression coefficients in our analysis or in our model would be non-zero. So we could kind of think about it from that perspective as well. So thus far, we've seen that the R-square value is 0.685. Again, we would say that the set of predictors account for about 68.5% of the variation in satisfaction. And from the results of our F-test is indicating to us that we should infer that the population R-square is greater than 0. Now, you'll also notice then in terms of our analysis that we also have this adjusted R-square value that's given right here. So basically, the R-square value is going to be a positively biased statistic, particularly in those cases where we have a smaller sample size and along with a larger number of predictors. So oftentimes what will happen is that the R-square value that we have computed and we were just talking about, it may overestimate the true population R-square value. So the adjusted R-square is kind of a computational approach to sort of adjusting that R-square down to kind of provide a more calibrated estimate of the population R-square. So when you're reporting on results, it's good practice to report not only on the R-square value, which, by the way, that R-square value is being tested using that F-test, but also to report on the adjusted R-square. And, in those cases where there's not a whole lot of difference between the R-square value and the adjusted R-square, then in those particular cases, you might one possibility is to just stick with reporting on the R-square value. But particularly when there's a more of a discrepancy between these two, then you definitely need to report on both the R-square value and the adjusted R-square. So as we're looking at our results, you'll also notice that we have our this is basically an ANOVA table right here. This is just giving a breakdown of the variation in our satisfaction measure, our dependent variable, into variation that is due to the regressors and also variation that is due to prediction error, or basically the residuals. So you'll see in this table right here, we have sort of a source, which is referring to the model, which is capturing the predictors, and then the residual, which is reflecting prediction error. So in this column right here, these are sums of squares. So in other words, if I go back and, in an introductory stat class, you oftentimes are exposed to sums of squares when computing the variance and standard deviation of a variable. So basically, what we have right here, this is the total sum of squares in terms of satisfaction. And basically, we can break that down into a portion of that variation that is attributable to the predictors, and the other portion that is due to what is not predicted, basically the residuals. So in terms of this table right here, you'll see that we have the model sum of squares. So that's the sum of squares due to the regressors or predictors in the model, and then we have the sum of squares due to the residual. So then if we sum those two values up, it gets us the total sum of squares right here. And one thing to note is that if we were to take the sum of squares for the model and divide by the total sum of squares, that actually gets us the R-squared value that we see right here in our table. So basically, it's just taking a ratio of the sum of squares due to the regression to the sum of squares total, and that gets us the R-squared value that you see right there. You'll also see in terms of the model description in this table, we have degrees of freedom. The degrees of freedom for the regressors or for the model right here is 3. That's equal to the number of predictors in our model. And then the degrees of freedom residual right here is just equal to the total sample size minus the number of predictors minus 1. There's 24 observations in our data set. So if we subtract 3 for referring to the number of predictors minus 1, that gets us down to 20 degrees of freedom that you see right here. if we form a ratio of the sum of squares to their respective degrees of freedom, we have this other term over here. These are mean squares. So basically, that's all it is. It's just basically the sum of squares due to the regression divided by the degrees of freedom due to the regression. That gets us the mean square due to the regression. And if we divide the sum of squares due to the residual by its degrees of freedom, we get the mean square due to the residual. And basically, all this, if we unpack this a little bit further, if we just take the mean square due to the regression and divide by the mean square due to the residuals, then that actually is what produces the observed F value that we see right here. That's the 14.53 that we have right there. So that's kind of the mathematical foundations behind this. When it comes to the actual interpretation of the results, typically we don't get into that level of detail, but that's just kind of where that F value is actually coming from, that F value that we see in our output. So at any rate, just kind of a little bit of a recap. As we said before, the R-square value is 0.685, and we have a significant F test value. So that's basically, both of those are indicating that the predictors appear to be accounting for significant variation in our satisfaction variable, which is our dependent variable. So the next step when it comes to the actual interpretation is to go into interpreting the individual regression coefficients. So that's where we're going to go down to this little table below. So in this table right here, we have a breakdown of the individual regression coefficients associated with the predictors. And we also, in this column right here, the coefficient column that you see right here, these are unstandardized partial regression coefficients. And what they're doing is they are reflecting the predicted amount of change in the dependent variable per raw score unit increase on a predictor. So that's basically how you would interpret or make sense out of the unstandardized regression coefficients. You'll notice too that we have the standard error associated with each of our regression coefficients. And if we form a ratio of the coefficient to its standard error, that produces the observed t value that you have right here. And so this t value, we can derive from that a p value, which is utilized in order to carry out our test, our significance tests for our individual predictors within the model. So as we're looking at this then, you can see that we have, for the age predictor right here, we have a negative regression slope. It's a negative 1.153. And basically, in terms of interpretation, we could say that for every 1 unit or every one year increase on age, there's a predicted decrease of 1.15 on satisfaction. So, and the reason why we can say that is because we have a negative regression slope. So that value right here is negative. It's at negative 1.153. So that's telling me then that for every 1 year increase on age, there's a predicted drop or decrease in terms of satisfaction. And so the amount of predicted decrease is 1.15. So, if we happen to have a regression slope that's positive, we would be saying that for every 1 unit increase on the predictor, there would be a certain amount of increase, the regression slope increase with in terms of the predicted change on Y. So that's the way to kind of think about it. So it just so happens that for this particular example, all of our regression slopes happen to be negative, which are signifying that we have negative predictive relationships between each of our predictors or independent variables and satisfaction. Now, keep in mind that, going back and thinking about this partial slope right here, this is, like I said, the predicted change on Y, or the predicted change in satisfaction per 1 unit or 1 year increase on age. And this is also controlling for the other predictors in the model. So we're holding all the values on the other predictors constant. So at any rate, we see right here that the regression slope, it's negative. And we also see, if we utilize maybe our standard 0.05 criteria, if we compare this p-value that's given right here of 0.001 against the nominal alpha of 0.05, then we would basically reject the null hypothesis, the null being that the population regression slope is equal to 0. So we would reject the null hypothesis and infer that the population regression slope is not equal to 0. If we look then at our next predictor in our model, we have severity. And you can see right here that we also, again, we have a negative regression slope. And so, in terms of interpreting the meaning of it, we could just basically say that for every 1 unit increase or 1 raw score unit increase on severity, there's a predicted decrease, because again, we have a negative regression slope of 0.265 raw score units on satisfaction. And this is, again, holding all of the other predictors in the model constant. In terms of whether this is significant, we can go back over here and look at the reported p-value. You see right here that the p-value is 0.631. And so this is clearly greater than our nominal alpha that we are testing with. And so because of that, we would basically say that the predictor is non-significant. So even though there might seem to be a negative predictive relationship between severity and satisfaction, it turns out it's not a significant predictive relationship, because the p-value that's printed out right here is greater than the nominal alpha of 0.05. So in terms of the anxiety predictor, you can see here that it is also in negative, and we also see that it is significant because the p-value is less than 0.05. So in terms of the negative predictive relationship, if we look at that coefficient for anxiety, that coefficient again is negative 15.59, roughly thereabouts. That would basically mean that for every 1 raw score unit increase on anxiety, there would be a predicted decrease, because our coefficient is negative, of 15.59 on satisfaction. And again, that's holding the other predictors in the model constant. Now, the next thing I want to draw your attention to is that we can actually generate standardized regression slopes very easily. And that we can do that by rerunning our analysis through this menu right here. And under reporting, we can select standardized beta coefficients. So when we select this and press OK, you'll see that now we get a column of those standardized regression coefficients. So that's under this column right here, it says beta. So in other words, what the standardized regression coefficients are indicating is basically the predicted change in standard deviation units on the dependent variable per standard deviation increase on a predictor. And again, we're holding the other predictors constant. And oftentimes the beta coefficients are utilized to sort of rank order the predictors in terms of their relative contributions in the model. And so basically, if we take the absolute value of these coefficients for our predictors, we might then rank order them in terms of their relative contribution. So we might say, because age, the largest beta coefficient in absolute value is for age at a negative 0.657, followed by the coefficient for anxiety. The coefficient value is negative 0.29, roughly negative 0.294. So that's the next largest value, then followed by the coefficient value for severity at about a negative 0.08. So that's obviously the smallest in absolute value. So in terms of, if we were going to rank order the predictors using these coefficients, we would say that age is contributing most in terms of its predictive power, followed by anxiety, followed by severity. Now, when it comes to looking at these regression coefficients and trying to kind of talk about their relative contributions, various authors have criticized the use of of these regression coefficients in this kind of way when you're assessing for relative predictive power. So there are other approaches that one might take in order to assess the relative contributions of the predictors within a model. But this is kind of one approach that's oftentimes utilized. I do want to mention too that I've actually put together a little PowerPoint on this kind of walkthrough of our data and our model and so forth, and I'll include a link to that underneath the video description. And I talk a little bit more about other possible approaches to assessing relative importance. One of them is using the squared semi-partial correlation. So be sure to go under the video description and check that out. So next, what I want to do is kind of show you one thing that you might want to utilize is, instead of using just the drop-down menu, you might choose to use syntax. So as I was kind of going through, you'll notice that when I was generating my output, you'll notice that as part of the output, we actually have syntax associated with these regression models. So the basic syntax for running a linear regression in Stata is to type in regression, or excuse me, to type in regress. So that's the function name, followed by the dependent variable, followed by each of the independent variables. So we have age, severity, and anxiety right here. So by typing those in to the command line down at the bottom, we can actually generate our results. So if you happen to learn some of the syntax for these different functions, a lot of times you can generate this very quickly just by typing into the command line. So for instance, if I go down to the command line, I can type in regress and then satisfaction, followed by age, followed by severity, followed by anxiety, and press enter, and you can see that we generate our results. The last one that we generated, we kind of ran our model right here, but you'll see that there's a comma followed by beta, and basically on this side of that comma, these are various options associated with our analysis. So if I go down to my command line, I can I can type in regress, satisfaction, followed by age, severity, anxiety, followed by a comma, and then beta right here, and hit enter, and we get our output. So you can see that, again, if you learn enough about how to use the syntax and so forth, you can run your analyses very quickly out of the command line. Another option too for running your analyses and now also keeping track of what you've done before, if you choose to maybe you want to go back and revisit what you've done previously, or you want to tweak an analysis and so forth, and you don't want to have to depend just on the command line. Another option is to use a do file editor. So if you go up here at the top, you'll see that where my cursor is, it's highlighting, it says new do file editor. So if I click on that button right here, this little editor opens up, and you can actually type your commands in, and you could save this file, and then later on, if you wanted to reopen it and go back and modify the syntax or add or whatever, you could certainly do that, and then you could run your analyses out of this. So for instance, if I wanted to go back and I wanted to save my original analysis without the standardized regression coefficients, I could just type in regress. I'll just go ahead and type in my satisfaction, age, severity, and anxiety variables right there. And and so to run this, I can just highlight it and click on execute selection or in the do file, and you can see that it runs the analysis. So basically, you can create larger batches of syntax that you can save, and again, you can call it up in future analyses if you have data in basically the same variables in a new data set or whatever. You can call it up, and you can run your analyses that way. So you don't have to type everything in the command line, or you won't have to use just drop downs for everything. I will say too that that in terms of other functions, one other one that you might think about when you're running your linear regression is looking at collinearity among your predictors. So basically, when you run your main analysis in Stata, there are actually sub-analyses or kind of ancillary analyses that can be carried out to look at various assumptions and so associated with your model, and you can generate additional output and so forth. And a lot of times this occurs through the use of the post-estimation commands. So like right now, I've run my analysis using linear regression. And one thing that I can do is if I go under statistics and then go down to the bottom right here, you'll see I've highlighted post-estimation. And so if I click on this, you have a post-estimation selector that comes up. And so you have a number of different options that are available in order to generate additional analyses. All of these too have syntax associated with them. So you could actually, if you again learn the syntax associated with them, you can plug them into the command line or plug them into the do file editor and be able to generate your outputs in that way. But for instance, one thing that you might do is if you might click on diagnostic and analytic plots, there's specification, diagnostic, and goodness of fit. One thing that you might click on is variance inflation factors. And basically, one of the assumptions in linear regression is that you have an absence of, kind of high levels of collinear or collinearity among your predictors, or, an absence of singularity. So basically, when you run your regression analysis, a lot of times, most of the time, you're going to have predictors that are correlated at some level. But ideally, you're not going to have predictors that are so highly intercorrelated that they're essentially representing the same thing, and that they are linearly dependent on each other. That's not a good thing when you're running regression analysis. So one way to assess that is through the use of variance inflation factors. And so you can access this option through the post-estimation box that you see right here. So if I click on OK, we've already selected variance inflation factors. If I click on OK, you'll see that it generates, again, there's my syntax right there. And then you can see we have a table that contains the variance inflation factors. So basically, variance inflation, one of the effects of collinearity among predictors is to inflate the standard errors in your regression analysis, and through that inflation, what it does is it oftentimes creates underpowered tests when you're testing the regression slopes for statistical significance. So basically, the VIF is just an indicator of the amount of variance inflation. Technically, it's the variance error, the inflation in the variance error. But if you take the square root of your variance error, that's what gets you the standard error for your regression coefficient. So the variance inflation factor values that you see printed out right here, you can basically consult these in order to kind of gain an idea about how much, whether collinearity might be a problem during your analysis. So there are various rules of thumb out there in terms of identifying predictors that may be collinear with other predictors within your model. One common rule of thumb is, if a VIF is greater than 10, then that may signify or signal that you have a potential problem with collinearity, or a problem involving collinearity with one or more of your predictor variables. So what we were looking at in terms of if we're using that particular threshold, you can see right here the VIF value for severity is 1.83. So clearly that's not greater than 10. So we would assume that at least severity is not collinear with the other predictors in the model. You can also see that age, the VIF is 1.61, and for anxiety, the VIF is 1.18. And so in both of those cases too, we're clearly well less than 10. So in this particular case right here, that would be an indication that collinearity is not really much of a problem, if a problem at all, in our analysis. So that's basically how the VIF works. You'll notice this value over here, this 1 divided by VIF, this is actually referred to as tolerance. And so, we could also establish, criteria for deciding on whether collinearity is a problem just by dividing, basically taking the reciprocal of the VIF. So basically, if a tolerance value is less than 0.1, then that would signify that you have a problem with collinearity with respect to a given predictor. So that's kind of the way to think about that decision. So obviously you can use either of those approaches when it comes to assessing your predictors for evidence of collinearity. Now, just to demonstrate the use of the command line, if I type in estat VIF, basically the estat is kind of a post-estimation command, and then we have whatever functions that we want to use. So if I type in estat space VIF into the command line and hit enter, you can see there's our variance inflation factors and tolerance values associated with each of our predictor variables. Okay, so the last thing I want to show you is just another few indices that could be useful for assessing the relative importance of predictors in your regression model. As I was kind of indicating earlier, we can't go into all aspects of multiple regression. There are just tons of decision trees that we could theoretically go down, and a number of different options for assessing assumptions and so forth. So I'm just keeping this relatively simple, but I will mention that one other approach for assessing relative importance of the predictors, if we don't want to just rely solely on the standardized regression weights in order to make that judgment, one thing that we can do is we can request partial, semi-partial, and then also squared partial and semi-partial correlations. So to do that, I'm going to go down to the command line right here, and I'm going to type in PCORR, and then I'm going to type the name of my dependent variable from the regression analysis. So I'll type in satisfaction right here, followed by the names of my predictors. So I'll type in age, then severity, and then anxiety. So when I hit enter, you'll see that I get a table that contains partial correlations, semi-partial correlations, squared partial correlations right here, squared semi-partial correlations right here. And you'll also see the significance values right here associated with each of those. And basically the significance values are going to correspond with the significance values that we saw in our regression table for when we were testing the individual predictors. One index that I particularly like to utilize when it comes to assessing relative contributions is this squared semi-partial correlations right here. So basically, you could think about it this way. If we have the total variation that we're trying to account for in our satisfaction dependent variable, then what we can do is we can compute the unique proportion of variation in satisfaction that is accounted for by a given predictor. So, to give you sort of an example of what I'm talking about, let's just assume that we have, and just to kind of keep things really, really simple, let's pretend like we are running a regression and we only have two predictors. So this is just to kind of highlight a concept right here that I want to show you. So imagine that this is my dependent variable y, and imagine that I've got, a first dependent variable right here. We'll call this x1, and a second dependent variable, independent variable, which is x2. So we have x1 and x2 as predictor variables. So as you're looking at this, you can see that the total variation in in the dependent variable is reflected in this circle right here. It's a little hard to draw, but there it is. So the R square value is reflecting all of this area right here. So if I highlight all of this area of overlap between x1 and x2 and y, all of this area right here is captured by the R square value. If I take that area and divide by the total area in the dependent variable, that is essentially my R square value. So as we're looking at this, you can see that part of that area is uniquely accounted for by x1. So if I look at this area right here, this area reflects area that or association between the predictors and y that is unique to x1, that first predictor. This area right here is area that is accounted for in y that's uniquely reflecting the effect of x2. And then this area right here, this is basically kind of redundant variation. So in other words, we can't really attribute that variation to x1 or x2 because both of them are jointly contributing to that area. So when it comes to computing the squared semi-partial correlation, you can basically think about it as reflecting the proportion of variation in y that would be accounted for, like in this case right here, by x1, and this area right here by x2. And we're not really accounting for that area that is kind of redundant. The R square value captures all of that area, both the redundant and the unique variation accounted for by the predictors. But if I square the semi-partial correlation, what that's reflecting is the proportion of variation in the dependent variable that's uniquely accounted for by a given predictor. So with that said, if I go back and I look at my little table down here and look at the squared semi-partial correlations, you can see that the squared semi-partial correlation for age is 0.2684. If I multiply that by 100%, then I can basically say then that that age uniquely accounts for about 26.84% of the variation in satisfaction. If I look at the squared semi-partial correlation for severity, multiply that by 100%, you can see that it would be roughly 0.4 or 0.4%. So in other words, severity would be accounting for about 0.4%, or uniquely accounting for about 0.4% of the total variation in y. If I look at the squared semi-partial correlation for anxiety, it's 0.0729, multiply that by 100%, and we can say that anxiety uniquely accounts for about 7.29% of the variation in satisfaction. So with that said, then we can we can sort of rank order those predictors in terms of their relative contributions, in terms of the unique variation accounted for in the dependent variable. And so this is kind of one possible alternative to using just the standardized regression weights in order to kind of rank order the relative predictive contributions of our predictor variables. Okay, so at this point, I'm going to stop the video, and like I said, the aim was not to go into all aspects of multiple regression. There's just lots of different ways that we can, lots of different things that we could be covering. And so I just wanted to give you this sort of general overview of linear regression using Stata. And so I've kind of gone through just using some of the drop-down menus, going through some of the interpretations and so forth, and a little bit on syntax. But if you want to, again, as I said before, you can download a copy of the PowerPoint that I put together for this presentation by following the link that's provided underneath the video description. So thank you very much for watching, and y'all have a great day.